algebra students, we are still in 1.9. We're going to finish up with example 3. I remember this particular example from last year, and it definitely shows up in geometry. This is kind of some upper level thinking. When you take geometry, those that are actually taking geometry, maybe you're going to Coastal next year, you'll take this in your geometry class. You'll hear it and actually experience it in geometry. I remember teaching this when I taught geometry a couple years ago. And Math 1 students going into Math 2, you're going to see this again, is my point. So example 3, this is what it says. Every dimension of a 2 by 4 inch rectangle is multiplied by 1.5 to form a similar rectangle. So let's just stop right there. Here's the original rectangle that they're talking about. There's the 2 by 4 inch rectangle. And what they did was they multiplied the 2 and by 1.5 to form a similar rectangle. So 2 times 1.5 will give you 3, and 4 times 1.5 will give you 6. That's what they did to get that, okay? So I just wanted to point that out to you. These are similar. I'll do the little squiggle line so you can see them. Triangle A, or excuse me, rectangle A is similar to rectangle B. And they used a scale factor of 1.5. They multiplied the dimensions, each dimension by 1.5 to get the new dimension and the new rectangle, okay? So if you multiply by a number that's greater than 1, that's going to give you a figure that's bigger. So any number bigger than 1 is going to enlarge the figure, okay? So greater than 1 enlarges, less than 1 shrinks, okay? In this case, because we are multiplying by 1.5, that's bigger than 1, so triangle A becomes triangle B. B is larger, and that's it enlarged, okay? Now, how is the ratio of the perimeters related to the ratio of the corresponding sides, and how is the ratio of the areas related to the ratio of the corresponding sides? So we have some questions to answer. Let's go down to the ratios. First of all, we can do the sides right now because we see the sides very clearly, okay? If we start with rectangle A, this is the pattern we're going to follow. We're going to do rectangle A over rectangle B, and we're going to do that in each of these ratios. That's the pattern. We're not going to switch the pattern. Our top number will be a number from rectangle A, and our bottom number will be a number from rectangle B, okay? So looking at the sides I've circled, rectangle A, we've got 4 over, and what matches up to 4 is 6. And if we reduce this particular fraction, reduce top and bottom by 2, we'll end up with 2/3. So circle that. Let's hold on to that information, and we'll tuck it back in later. We'll use it a little bit later when we answer the questions. Okay. Now perimeters, I actually set up a chart here for you to help you with the perimeters. So we're going to fill in this chart. We want to first find the perimeter of rectangle A. And just like I told you, this 2L plus 2W, I did an italicized L. It looks like a 1 that's slanted slightly to the right. It's not a 1, it's an italicized L. That means length. W is width. So we've got 2 times 2 plus 2 times 4, okay? So we substituted in the measurements for length and width. Length is 2, width is 4. 2 times 2 is 4, 2 times 4 is 8, 4 and 8 is 12, okay? So that's important, circle that. Now for rectangle B's perimeter, we're going to do 2 times 3 plus 2 times 6. 2 times 3 is 6, 2 times 6 is 12, 6 and 12 is 18. Okay, so let's go down here to the ratio right here. Perimeters. We now know the perimeter for A is 12, and we know the perimeter for B is 18. 12 over 18. Now let's reduce that just like we did for the sides. Let's reduce it. So what number reduces both 12 and 18? Let's do 6. 12 divided by 6 is 2. 18 divided by 6 is 3. Circle that. Hey, wait a second. The ratio of the sides is 2/3, and the ratio of the perimeter is 2/3. So let's answer this question right here. How is the ratio of the perimeters related to the ratio of the sides? The easiest answer is they're the same. It's the same exact ratio. So if you find the ratio of the sides, you automatically know the ratio of the perimeters because they're equal. They're equal. All right, good job. Okay, let's do area, length times width. So this is real simple. 2 times 4 is 8, so circle that. 3 times 6 is 18, circle that. So we have 8/18. And what we're going to have to do for this one, remember we're going to do A over B again. So A is 8, B is 18, and we want to reduce it. Now the best way I can reduce this is with a 2. That's fine. And that's going to give me 4/9. Now you're like, oh, it's not following the same pattern. I didn't get 2/3. Well, wait a second. There may be a way to get 2/3 out of 4/9. And so it may require squaring some numbers. What number do you square that will give you 4? Okay, 2. What number do you square that will give you 9? 3. Now take a look at that. That's very interesting because 2/3 squared gives me the area fraction right here. So if I square 2/3, I'll have the area ratio, which is really neat. So that answers this question. How is the ratio of the areas related to the ratio of the corresponding sides? All I have to do is square the ratio of the sides, and I'll have the ratio of the areas, which would be 4/9. So if in another problem, for example, if the ratio was 3/5, then the area ratio would, all you do is square 3/5, be 9/25. So that's how you would do that. But you would end up with 2/3 in all of them. Just with the area, it would be 2/3 squared. So for the area, it's the ratio squared. All the rest of them would be equal. So that's a little bit very high upper level thinking, okay? And I've had students that are like, oh man, I did not understand at all what you did there. And that's completely understandable. I feel your pain. I really, really do. If you need to go back and listen to me again, rewind. This is such foreign information, it might be worth hearing 2 and even 3 times. You don't have to do it 2 and 3 times in a row. Maybe take a break and come back to it. That might be the best way to handle that. All right, so now we're going to talk about cylinders. Every dimension of a cylinder with a radius of 4 and a height of 6 is multiplied by 0.5 or 1/2 to form a similar cylinder. So remember what we said, when you're multiplying by a number less than 1, so our first cylinder is going to be bigger than the second one, okay? So here we have a radius of 4 and a height of 6, and then when you multiply that cylinder by half, you're going to have a smaller, because remember, the figure's going to become much smaller when you do that. So we'll have a 2, and then we'll have a 3 here, because we cut it in half. So the radius will be half, and the height will be half. So now what they want us to do is compare the ratio of the volumes and relate that to the ratio of the corresponding dimensions. So I'm going to call this one A and this one B, okay? And let me just make sure I'm following suit in the book. Yeah, the big one's A, the little one's B. All right, so let's take a look. Now the radii, that's going to be this up here, okay? That's half of the circle, half of the diameter. So we're going to follow suit. We're going to do A over B. So what's the radius in A? 4. What's the radius in B? 2. And so we're going to end up with that ratio 2 over 1. If you simplify it and keep it as a fraction, it's going to be 2 over 1. Okay? Now what do you think is going to happen to the heights? How do you think the radius and the height ratios are going to turn out? Do you think they'll be different? Do you think they'll be the same? What do you think? All right, well, let's let the numbers do our thinking for us. Let's see if the numbers back up what our thought process is. Okay, so A, the height is 6. In B, the height is 3. And so we're back to 2 over 1 again. See there? They're identical. If you thought, oh, I think they're going to be the same, like in the other example, the side ratios versus the perimeter were the same, you are absolutely correct. Good job. Okay? So now we want to look at how is the ratio of the volumes related to the ratio of the corresponding dimensions. Okay? The dimensions are 2 over 1. So we want to see what happens with the numbers for the volume. Let's just see, okay? We got to calculate it first. So we've got pi r squared h, pi r squared h. So we're going to leave pi as pi. I'm not going to convert it to 3.14, okay? So I'm going to go ahead and tell you, leave pi as pi. Just almost treat it like a variable, okay? And not turn it into a number. So in cylinder A, we're going to do 4 squared, there's your radius squared, times your height, times pi. So we're going to just leave pi alone. Go ahead and do 4 squared, you guys know that's 16. And then we're going to do 16 times 6, which is 96. So we're going to leave this as 96 pi. We're going to do the same thing with cylinder B. We're going to do radius squared times the height times pi, leaving pi alone, just leave alone. 2 squared is 4, 4 times 3 is 12, okay? Now, we have the two volumes, so we're going to do A over B, just like we did with the other two. And we have 96 pi is the volume of A over 12 pi, which is the volume of B. Okay, so we need to examine these numbers. Okay, so let's go ahead and reduce it and see what happens. Looks like I could reduce top and bottom by 12. So I'll end up with 8 over 1. Now, 8 over 1 is not 2 over 1, but think of a way that we could get to 8 using the 2. Because remember in the other example, you know, we had 2/3. And if we squared it, we would get 4/9, which was the ratio of the area in the other one. Now, volume's weird. Volume is measuring 3 dimensions. It's weird. Because when you think about area, area is length times width, which is 2 dimensions. That's why the exponent for area was 2. Volume, you're measuring 3 dimensions, length, width, and height. Okay, so that would mean, what would I have cubed? What would I have cubed that would give me 8? What number times itself again would give me 8? And if you're thinking, oh, that would be 2, you're exactly right. So for area, if I square the ratio of the sides, I'll get the area ratio. For volume, if I cube the ratio of the sides, I'll get the ratio for the volume. Okay? So remember, area, you square the side ratio, because there's two dimensions. Area is only two dimensions. Volume, you would cube, raised to the third power, cube the side ratio. That's the difference between the two. Now, I don't have any bonus for this. This was hard enough. I don't think you could have gotten this unless I guided you through it. But this was really, really hard stuff. This is like top of the line, really critical thinking. You're seeing relationships between area and volume in different figures, and seeing that indeed there is a pattern. And you could memorize the pattern, and then you would always know and could figure out the answer pretty easily, or you could figure it out using your numbers to drive your answer. So I'm sorry this was so hard. I do want you to try one, just not in the example. We'll probably do it as classwork or homework, and maybe group work or something to you guys can talk it out. This is something I definitely, if you want me to go over this again, let me know, and I'll be happy to talk you through this and do some live teaching on this with you again. If you would like that, mark that on your paper so you remember to ask me about it. Okay, so if you have questions, put your questions in the margin. If you need to see this again, maybe put a big asterisk and say, ask Mrs. Thompson to go over this again. Something to draw your attention back to these notes so that we can discuss this one more time. Great job. Thank you for your focus and attention, and I will see you in class. Thank you for listening.